This week, we're going to build on the foundations that we set last week when we constructed one sample confidence intervals. This week, we'll have the exact same concepts, except now for two samples. So our point estimate will be a little bit different because we'll have to find the difference of two samples for the most part. But the rest of it's going to be pretty similar to what we learned last week. Obviously, the formulas will be a bit more complicated, but we're going to use the same concepts. So we're still going to use the same Z star or the same T stars, those critical values that we found last week for means where we know sigma or where we don't. And you'll notice this time around we have unequal variances or equal variances. And then of course we have for paired means, which is something new, and then for two proportions. When we learned about confidence intervals last week, we started out with the basic formula that said let's take the point estimate plus or minus the margin of error. And that's exactly what we're going to have this week as well, but as you can see, everything's going to get just a little bit more complicated. So when we're dealing with a point estimate, for the most part, we're going to be subtracting two means. And you can see that I have the subtraction of two means and the subtraction of two means and the subtraction of two means. And then I've got this guy here that's a little bit different, and we're going to talk about him. But then here I have the difference of two proportions. So really that point estimate is going to be subtracting two means or subtracting two proportions. The only difference is if you have a paired means question, we're going to have a question where the data is not independent. So for instance, a pre-test, post-test, a field before it's sprayed with fertilizer, and then a field after it's sprayed with fertilizer. So the results or the outcomes will not be independent of the first set of data, and therefore we're going to be concerned about the differences between the two pairs of data. So this one's actually going to look a lot like last week when we had the one sample T, and that's exactly what we're going to be doing here again, a one sample T interval, except we're going to have to find the differences to find the one sample. Now, as you can see, the right side, the margin of error, also got a lot more complicated. So we're still using the same Z star or T star in the same situations, but now because I have two standard deviations, two sigmas or two standard deviations of the sample, things will get a little bit more complicated. But again, we're just going to use these formulas and make Excel do all of that work for us. So you might look at this and feel a little bit overwhelmed because there's just kind of a lot going on. But please don't be overwhelmed because again, and I'm just going to erase all of this just so you have a nice clean page if you want to take a screenshot of it. So that we can use these equations in Excel to do all of the work for us. So the only thing that we're going to need to use special functions in Excel for is finding these values, and we learned how to find those last week. So again, this week should be pretty straightforward. Let's take a look at our first question, and before I get started into how I've set up Excel and what the question is asking, I really want to talk to you about the fact that remember that I'm helping you with how to set this up in Excel, but it's more important not that you can regurgitate what I have written in Excel, but that you understand what I have done. Because, for instance, when you do this on the project, you're going to need to know how to use the exact cells that I've given you. So maybe I don't have a place for you to put the standard error. You're going to need to understand how you can compensate for that. So make sure that you're striving to understand the material and not just copying my formulas to make it easier for you. So really try to do the work and put in the time. So let's take a look at the formula. Remember, this is a formula for sigma known. So that just means that we have a population standard deviation that's known. The way that I'm setting up my cells is that these cells will be input cells. These are things that I'm going to get by reading the question. And then these cells are going to be computed for me based on those values. Now, it's not rocket science what I'm doing here. What I'm doing here is I am essentially using this formula that I've copied from the other page and I'm just going to let Excel do all of the work. So the point estimate is just this very first part, x bar 1 minus x bar 2. That's this guy. That's the point estimate. So as you can see in my formula, I've set it up to be the mean 1 minus mean 2. That's exactly what the point estimate is. The right side of the equation, the margin of error, is made up of two parts. The first part of the margin of error is the critical value. Now, we learned how to find this last week. Because we know that sigma is known, we're going to use the normal model. When sigma is unknown, we have to use the t model. So using the normal model tells me that when I'm finding my critical value, I'm going to use norm inverse or norm S inverse. Now, it's also important to know what value do I need for the norm S inverse. So if I think about that normal model, and this question asks for a 95% confidence interval, that tells me that 95% of the data is in the middle. So if I take 1 minus C, I'm going to get alpha. So 1 minus 0.95 gives me an alpha of 0.05. And what I know is that this guy is separated into each tail. And so there's half of 0.05 or 0.025 here, and there's half of 0.5 or 0.025 here. Now the reason I bring this up is because when I'm looking for the critical value, I need either this value, which is obviously 0.025, and then find the norm inverse of that. But the problem with this guy is that it's going to be negative. So you can do that. You can use exactly what I have here and just use the negative in front, and you won't have to add this B7, but I'm going to show you how I did it. I'm taking 95, which is what's in this cell, the confidence level, and then I'm adding 1 minus that value divided by 2. That's this. 1 minus 0.95 and then divided by 2 gives me this much. So if I take 0.025 plus 95, that gives me 0.975, and that's going to give me the positive critical value. So that's what I've done here. Okay, so that leaves us with the last part of our margin of error, which is what we call the standard error. And again, your book does not call it that. So if you don't have a space for standard error, you know that you just have to build that in when you're doing margin of error instead. So for the standard error, I'm going to take each given population standard deviation, and I'm going to divide each of those by their respective sample sizes, N1 and N2. I'm going to add them together, I'm going to square them. And the reason that we square them, in case you're interested, is we cannot add standard deviations. We can only add variances, and the variance is the standard deviation squared. So essentially, I'm taking the standard deviation and squaring it, dividing it by the respective sample sizes, then adding them together and taking the square root to turn it back into a standard deviation. All of that's going to go here. So again, that formula would be exactly what I'm done here, which is the square root of the standard deviation squared divided by the sample size plus the standard deviation squared divided by the sample size. And then the margin of error is just multiplying those two values together. And then this plus minus now comes into play because the lower limit is the point estimate minus the margin of error, and the upper limit is the point estimate plus the margin of error. So now let's take a look at which values go where in my inputs. So remember, I'm just looking for the difference between the two values. So for the first part, it says we have freshmen, 42 freshmen. So as I go through this, I'm going to input the values as I go. So 42 freshmen, that's going to be my first sample. A mean study time of 15 hours per week. A random sample of 39, that's a sample size, 39 seniors, reported a mean study time of 23 hours, that's my second. And then I need a 95% confidence interval, so make sure you put 0.95. And the study times for freshmen have a population standard deviation of 4.7 hours per week, and then 5.2 for seniors. So really, once you have everything set, all you have to do is input the values, and then you have to understand what you found. So don't just say, here's my confidence interval. What does this mean? So essentially what we have found is the confidence interval goes from negative 10.16 to negative 5.836. How do I interpret that? What does that mean? Well, that means I'm 95% confident that the true difference, because remember, we're just basing this on a sample, and I want to know the true difference between how much time freshmen spend studying versus seniors. And because this is negative, what does that tell me? Does that mean seniors study more or freshmen? It all goes back to how you started the question. So when I started the question, this was freshmen. This was seniors. So if I took freshmen minus seniors and I got a negative value, that means this guy was bigger. So when I interpret this, I'm going to say, I am 95% confident that the true mean difference of study time between freshmen and seniors is essentially that seniors study 10.16 to 5.836 hours more, or that freshmen study 10.16 to 5.836 hours less per week than seniors. Let's take a look at another example. In this example, we will not be given sigma, the population standard deviation, and we're going to assume unequal variances. So you'll know that this is going to be something that you'll have to look for, is whether the variances are assumed to be equal or unequal. Typically, it will tell you assume the variances are equal if they want you to assume that they're equal. In this case, we don't know anything about their variances, and therefore we're just going to assume that they're unequal. So, as I'm looking at the functions, you'll notice that this is exactly what I had on my last example. The upper limit is the point estimate plus the margin of error, and this is the point estimate minus the margin of error. The margin of error is still found by taking the critical value, in this case it's a t star as opposed to a z star, times the standard deviation of the difference, or standard error of the difference, and we're going to talk about those formulas in a moment. The point estimate should look the same, so it's still mean 1 minus mean 2, but we need to talk a little bit about the other three. So first let's talk about the degrees of freedom. So hopefully you've learned, as you've been working through Hawks, that the degrees of freedom for a question where the sigma is unknown and there are unequal variances, the degrees of freedom is simply the lower of the two of n1 minus 1 or n2 minus 1. So it's whichever one is smaller. So I'm going to show you the function that I used, and you don't have to do it this way. So if you are like, oh my god, please don't give me another formula, really you don't need to. You can just find those values yourself in your head and enter the degrees of freedom. So here's the way that I did it, because I'm lazy and I just like to have Excel do everything for me if I can. I'm using the if function, and the if function, as you can see here, has logical test, value if true, value if false. So the logical test tells Excel to compare two values in this case. So I'm saying, please compare B3, which is N1, and B6, which is N2. And if B3 is greater, well, that's the one I don't want, right? If B3 is greater, I want the one that's less than. So I want B6 minus 1. So that's what I've done here, is I said, if that value is true, if B3 is bigger, then give me B6 minus 1. If B3 is not greater than B6, then that's the one I want. Give me B3 minus 1. And that's going to be my degrees of freedom. So again, don't feel like you have to use that, but please feel free to use it if you'd like. The point estimate we already talked about is the same. The standard error of the difference is going to look the same as last time, except of course we're using standard deviation instead of sigma, but really it's the same thing. And the critical value is the other major difference here, because when you are dealing with a means question where sigma is unknown, then you have to use a t-inverse instead of a norm inverse. But I'm still using that same formula where I said, okay, let's take B7, let's take the confidence level, and then add 1 minus the confidence level divided by 2 to that. And the other part of a t, because it's not just the probability, the other part of a t is that I also need the degrees of freedom. And so, of course, I've pointed that cell to B9. So let's take a look at how this one turns out, and then, of course, the most important part, which is how to interpret our results. So Misty is taking a class. She thinks it's all the teacher's fault that she's not doing as well as she should, which we all think that way, right? So she collects exam scores from people in her own class, and there's 11 people that she collected scores from, so that's N1. The mean for her class was 75, so that's mean 1. The standard deviation for her class is 8. Then she talked to people from another class with a more experienced teacher, and there were 9 people that shared their scores with her, and the scores had a mean of 82 and a standard deviation of 5. She wants to create a 90% interval, so 0.9. So again, once you have Excel set up correctly, then you can let Excel do all of the work for you. So my result, my response to this, is that my interval goes from negative 12.45 to negative 1.548. So just like we talked about before, keep in mind this is Misty's class, and this is the other class. So what does my interval mean? You need to know how to interpret it. Now, they're both negative values. And because they're both negative values, that means there is a difference. So if you have something where 0 is somewhere between the values, so you have a negative, comma, a positive, then we can't say with any confidence that there's a difference in the values. But because they're both negative, we can say that we're 90% confident that the mean exam score for students in the inexperienced teacher's class, which is Misty's class, is between 1.5 and 12.5 points lower, again lower because they're negative, than the mean exam score for students in the experienced teacher's class. So the true mean is somewhere in here. We're 90% confident that the true mean is between those two values, and because those two values are negative, we can sort of say that yes, Misty was probably right, that her teacher is scoring them lower than the other class. Let's take a look at another question and why we might use a formula for unknown sigma equal variances. So we're dealing here with birth weights, and we know based on the given information that the distributions of birth weights are approximately normal for both populations, but it doesn't say specifically that the variances are assumed to be equal. But again, we're dealing with a normally distributed variable of weight, and the only difference between the two samples is that one sample the mothers will have taken a pain reliever, and in the other sample they won't. So we can assume that those variances are equal. Now, variance again is just how spread out the values are. So that's why we're assuming that those values are going to be just as spread out in either distribution. A couple of things that we need to keep in mind here. The degrees of freedom is different, and obviously the standard error is quite different. So the degrees of freedom, instead of taking the smaller of the two, when we have equal variances, we are going to actually add the two sample sizes and subtract 2. So that's what I've done here, B3 plus B6 minus 2. The point estimate is still the difference of the two means. The standard error is all of this mess. And so I would just encourage you to copy down cell by cell exactly what I have here, because all I've done is essentially enter all of this in. But the issue that I see quite often is students who don't put parentheses in the correct place. So remember that Excel is just a calculator. And Excel is going to follow the order of operations whether you want it to or not. So notice here I've got 3 parentheses before I even get started. I have the square root, and it's kind of nice because Excel color codes them for you. So this first parenthesis is black, and then this last parenthesis is black. So it's kind of closing, I'm sorry, this last parenthesis is black, so it's closing off that parenthesis. And then I've got a red one, and then you can see that's the end of the red one. And then I've got a purple one, and you can see that's the end of the purple one. So keep those colors in mind as you're going. I want N1 minus 1, so that's B3, that's my first sample size minus 1, times the standard deviation squared. And then I'm going to add to that B6 minus 1, so the second sample size minus 1 times B5 squared. But now keep in mind, I want all of that to be the numerator, so that's why I've used the red parentheses so that Excel knows that that's the end of the numerator. And I want to then divide that by N1 plus N2 minus 2, which is the same as the degrees of freedom. So I just used B9, but you could enter parenthesis, B3 plus B6 minus 2, either way. And then I want to multiply, so notice I've closed that parenthesis, and then I'm multiplying by the square root of 1 divided by B3 plus 1 divided by B6, so that's just the 2 sample sizes. So that's all of this stuff. That's the standard error. The critical value, again, oops, don't mess it up. The critical value is just as we did last time. Again, make sure you point it to the degrees of freedom as well, but I'm really just using the t-inverse of the confidence level plus 1 minus the confidence level divided by 2, and everything else should be the same. So let's take a look at this question. The mean 1 says we have 12 mothers, okay, so that's N1. Got a little delay here. N1 is 12. And those are the mothers who took the pain reliever, and it calculates the mean birth weight of their babies was 5.6, and the standard deviation is 1.8 pounds. And mean 2 is 20 mothers who did not take pain reliever while pregnant, calculates the mean birth weight to be 6.3 pounds, and a standard deviation of 2.1 pounds. We're going to construct a 99% confidence interval for the true difference between the birth weights. And then this part's super duper important. This is one part I'm really going to focus on. Does the confidence interval suggest that there's a difference in the birth weights? So calculations have all been done by Excel, and again, my interval, always from least to greatest, this one goes from negative 2.7 to positive 1.3. So this is our first one like this, where 0 is in the interval. Keep in mind, if 0 is in the interval, there's no evidence to say that there's a difference between the two distributions. So it doesn't matter that mean 1 was 5.6 and mean 2 is 6.3, and those aren't the same. What we're saying is they're not far enough away from each other to be statistically significant. So what I can say based on this, these results is essentially that the confidence interval does not suggest that there is a difference in the birth weights between babies of mothers who took the pain reliever and babies whose mothers did not. Again, because 0 is in the interval. Let's take a look at a different example now. Different in that the information that we're given is not independent. So in all of the examples up to this point, the two samples have been independent from one another. So if I look back at this first example, we're looking at the study habits of college students. So the study habit of a freshman is not going to be affected by the study habits of a senior. The test scores from one class are not going to be affected by the test scores of another class. The birth weight of one baby is not going to affect the birth weight of another baby. In this case, I have CPR students in a class who are given a pre-test and a post-test. These data are paired. It's the same student before and after. So 70 to 90, that's the same student. 71 to 83, that's the same student. The question is the differences that we can see between these pre and post-test values, are those differences statistically significant at a 95% confidence level? So essentially, and you can see that the equation that we're going to use here is different than the equation that we've used in all of the other examples because there's no subtraction here. And the reason that there's no subtraction here is because this D bar stands for the mean of the differences. So here's what I'm going to do. I'm going to calculate in this cell or in this column the differences of these two values. So between 60 and 80 and 79 and 63. Now I want to know the mean increase. So I'm going to take the post-test minus the pre-test. And typically you'll take the second value minus the first. And so I'm going to do that for every value here. And as you notice, I just copied and pasted it, and that value B6, B7, B7, A7, B8, A8, it copied down just as I wanted it to. Now these cells here are now going to calculate. So I've entered these values. So this one is just the average of this column. This guy is the standard deviation of these values. This guy is count, so it's just going to count the values. Sorry, a little delay in technology, but that's the count C2, C11. And then I just have the confidence interval. So I'm going to enter 0.95 here, and the rest of it's going to calculate. So the critical value, again, nothing new here. I'm going to be using the T inverse, and then whatever the confidence level is, and then 1 minus that divided by 2, and then again the degrees of freedom. So the degrees of freedom is just n minus 1. So you'll notice I didn't make a whole new cell for degrees of freedom. I could have said, okay, degrees of freedom is n minus 1, but instead I just chose to take F3 minus 1 in that value. So there's a lot of different ways that you can do it. This is just the way that I did it. The standard error is, again, just using the standard deviation of my sample divided by the square root of n. And then the margin of error, I've used m, I think E is what they use in the textbook, is just the critical value times the standard error. And then the lower limit and upper limit are calculated by taking the point estimate. So I used mean of differences, but if you wanted to write point estimate here, that's just fine because that's what it is. 16.8 is what we're expecting, and then E, so I'm subtracting 16.8 minus E and then plus E. And again, the question says, did the student's knowledge increase? So again, what is the interval? The interval is 14.2 to 19.4. As you can see, 0 would be somewhere down here because this is just a number line, right? So 0's here, and then 14.2 and 19.4, we're saying the true mean difference is somewhere between those two values. So if that's the case, then can I say with certainty that obviously that they have scored or learned a little bit more about CPR? Absolutely, because their scores went up somewhere between 14.2 and 19.4 points. 0 is not in that interval, so the research suggests that the class did increase the student knowledge based on their exam grades. Let's look at our last question now, and there's a lot of different ways that you can correctly set up your spreadsheet. So just keep in mind, as I said at the beginning of this video, that you need to know how to adjust things on the fly. So when you're doing your project, I might give you a space for critical error. I might critical value, or I might not. I might give you a space for standard error, or I might not. I might just say, here, what's the margin of error? And make you do it all in one big equation. So again, know how to do all of the parts on your own. Don't just give me back what I've given you in these videos. So let's take a look at this question. And on this one, I have purposely not filled in any of these formulas because we are going to fill them in together as we go. So again, all I'm doing, guys, is looking at the actual formula from your textbook that says, okay, to find the point estimate, we're going to take P1 minus P2. And again, that's P1 hat minus P2 hat. Hat just means that it is the value that we have observed. So to find P hat for my first sample, I'm going to take the number favorable divided by the total number. And then to get Q hat is just 1 minus P hat, and your book actually doesn't even call it P hat. Q hat, it calls it 1 minus P hat. So I'm just going to take 1 minus that. And then for B, my second sample, I'm going to do the same thing, number favorable divided by the total number. And then for 1 minus P hat, I'm just going to subtract that from 1. Now, the point estimate is going to be found by taking the difference of the P hats, P hat 1 minus P hat 2. So that's all I'm going to do here is subtract. The critical value, it's a Z, and that means we're using norm inverse. And in fact, I'm going to use norm S inverse, which just means I don't have to put comma 0, comma 1. And the probability, just like before, is going to be the confidence level, and then plus half of what's left over. So what's left over is 1 minus that same confidence level, and then I'm going to take half of it. And then the margin of error, so notice on this one I haven't given you a space for standard error, which is all of this stuff. So if I have to go straight to the margin of error, then I'm going to take my critical value multiplied by, and then I'm just going to enter the same thing I would if I had a space for standard error, which is square root, and then I need to take P hat 1 times 1 minus P hat 1 and divide it by N1, which is total number, plus P hat 2 times 1 minus P hat 2 divided by total number. And I didn't have to do anything crazy with parentheses there because Excel will go left to right with multiplication division and left to right with multiplication division, and then add those two values together, and that's what I want. So that's all I need for E. And then the lower limit will be my point estimate minus E, and my upper limit will be my point estimate plus E. So now let's enter our values. So we're looking at a new instructional technology, and we want to know if a larger percentage of students who use the instructional technology pass the class than those who do not. So there's 45 out of 50. And notice that's filling in the 0.9 and the 0.1. Those two should add up to 1. And then for the non-instructional technology students who passed, hold on, let me see. Records show that 45 out of 50 who were in the class, good, and then 38 out of 50 who were in the class that did not use it, so 38 out of 51. And I'm constructing a 95% confidence interval. And now Excel has done the rest of the work for me. Now, the solution, again, is 0.009, comma 0.30. So essentially that's 0.9% to 30%, excuse me. 0.9% to 30%, but where's 0? Again, if I were on a number line, 0's over here to the left because all of this is positive. So what conclusion can I draw? Well, I'm 95% confident that the percentage of students who pass the class is between 0.9% and 30% higher. So students who use instructional technology, on average, will score somewhere between 0.9 and 30.1. So the true difference is between 0.9% and 30.1%. So I can conclude that the instructional technology does improve student scores, again because 0 is not in that interval.